Okay, class, we're now going to begin a set of chapters on geosciences. We'll talk about the Earth, the planets in this chapter, and then we'll move on to such things as plate tectonics and the climate, the environment, and ecology, etc. Okay, but first let's talk about how old is the solar system and the Earth. What are the components of our solar system? How was our solar system formed? How was the Earth formed and the moon? Whatever happened to Pluto? And what are some of the other bodies that we see flying through the sky? Well, first, how do we determine the age of the Earth since we weren't back there at that time? We have to do this indirectly. And we actually determine this by determining the age of the oldest materials found on planet Earth, and then we then extrapolate that the sun must have been a little bit older than planet Earth. One of the ways of doing this is by radioisotope dating, and that's one of the reasons we talked about that in a previous chapter. But this type of radioisotope dating involves the conversion of uranium-238, an unstable isotope of uranium, to lead-206. It's called uranium-lead dating. And basically the idea is that there are certain rocks where lead is known not to be found normally, but that lead is only found in this rock or in this mineral if uranium-238 has undergone a radioactive decay sequence to convert uranium-238 to lead-206. Now, the complete sequence of these nuclear reactions is complicated. It's a 14-step process shown to the left, and not to worry about it. It's just that it involves a sequence of alpha and beta decays, which we talked about previously, and that the effective half-life for this process of converting uranium-238 to lead-206 is 4.5 billion years. Yes, I said billion years. Now, there are other methods as well of dating the planet Earth, but this is the one that works the best and that is most frequently used: uranium to lead isotope dating. One example of this uranium to lead dating involves the mineral zircon. Zircon is a crystalline material, and I show you to the right a photo of a particular zircon crystal that has been studied recently. And it is produced and zircon is a crystal formed as part of igneous rock, and we'll learn later on that igneous rock is formed as a result of the cooling of lava spewing out of volcanoes. Zircon is a very stable crystal material, and it's an example of one of these materials that will exclude lead from its crystal lattice. Now, that's a lot of science words, but basically it means that lead does not exist in the mineral zircon unless it is formed from uranium, because uranium will substitute for the element zircon in zirconium. So it's normal to find some uranium in zirconium, but the only way that lead is found in zirconium is if uranium-238 has undergone that nuclear decay sequence I showed you in the previous slide. So basically, lead's not supposed to be there unless it's through that decay process. And so, to give you an example, a few years ago in the journal Nature Geosciences, an international team of researchers reported that data that confirmed that the Earth's crust was formed 4.4 billion years ago, and that was the oldest mineral source, the zircon crystal, that had been discovered so far. They found it in Australia, and they used the uranium to lead dating method to determine its age of 4.4 billion years. Now, other dating studies with meteorites and moon rocks have led to a consensus value of about 4.568 with that degree of precision, 4.568 billion years as the oldest solid materials so far discovered in our solar system. The The zirconium we know, was formed on planet Earth. The others, moon rocks and meteorites, were outside of planet Earth that we happened to bring back to planet Earth, or that struck planet Earth as their meteorite. The sun then is thought to be at least 100 million years older, so we sometimes say that the age of the sun may be 4.6 billion years, and maybe the age of the Earth is about 4.568 to be more exact, billion years old. Now as an example of how this calculation is done, I'll have this slide, which you can print out at the end of listening to the lectures and take a look at the math which is shown here. And don't worry too much about it, except these are equations that were presented in the previous chapter on nuclear science and radioisotope dating. And in this example problem, I say, let's suppose you go on a hiking trip to Canada and you bring back a rock that contains zircon, and you take it to a laboratory and someone does an isotope dating analysis, and you find that it contains 10 grams of uranium-238 and 2 grams of lead-206. Remember that lead-206 should not ordinarily be there unless it was produced as a result of the decay of uranium-238. But with that information, the 10 grams and the 2 grams, you can plug into the equation as shown, plugging in the value of 10 for uranium-238 and the value of 2 for lead-206, and knowing the half-life for the decay of uranium-238, you could calculate that rock sample that you discovered was maybe 1.2 billion years old. So it was a relatively young rock compared to the one that the researchers found in Australia. Now, how about our solar system? What is the solar system anyway? Well, it's defined as a gravitationally bound system of the sun and all of its orbiting objects. Mouthful. The sun and its orbiting objects that are gravitationally bound to one another. Now, there are 8 planets. There are 4 terrestrial inner planets, Mercury, Venus, Earth, Mars, made primarily of rock and metal, and 4 giant outer planets, sometimes called the gas giant planets, Jupiter and Saturn, which are definitely made primarily of gas, but also Uranus and Neptune, which we sometimes call ice planets. Now, when we say ice, that really means frozen water and also other gases that are frozen, such as ammonia and methane, because it gets cold out there. In addition to the 8 normal planets that we talk about, there are dwarf planets. And here we find our Pluto. It has been demoted to the category of a dwarf planet, along with a couple of others, Ceres and Eris. Then there's some other smaller bodies, the asteroid belt that lies between Mars and Jupiter, mostly rock and metal, sort of debris, and also the Kuiper belt, which is a belt of asteroids beyond Neptune, and those are primarily thought to be chunks of ice. There are also planetary satellites. By that we mean like moons of Earth, of course, but also moons of the other planets. And some of the planets have rings. In fact, the 5 outer planets from Jupiter on have rings around them as well. And we'll talk a little bit about these planetary satellites in another lecture. So let's look at a more realistic representation of the distances involved in our solar system. Over to the left, of course, we have our yellow sun, and we can see the first 4 terrestrial planets, little small dots, Mercury, Venus, Earth, and Mars. And then we see the asteroid belt that we talked about, lying between Mars and Jupiter. And then as we go further out, you see that things get spaced out. You got Jupiter and then Saturn and Uranus and Neptune, and if we were to still give Pluto and if we were still to call Pluto a regular planet, we see that it would be further out from Neptune, although Neptune and Pluto do cross paths at some point. Now, in addition to the names and little representations of these planets, you see some numbers underneath each. And these are in terms of what are called astronomical units, an AU. Now, what that means is the distance between the sun and the Earth. And we call that one. We say that Earth is one astronomical unit from the sun. Now, of course, you probably have heard that it's 93 million miles or it's 150 million kilometers. But to make things easy, we just say it's one astronomical unit. Also, you might have heard, or we've talked about, we may have talked about how long it takes light to go from the sun to Earth, and we've said that that's about 500 seconds. So that if the sun were to suddenly, the lights would turn off in the sun, it would take 500 seconds, which is a little over 8 minutes, for us to even notice that the sun's not there anymore. So 500 seconds is the length of time it takes for light, the fastest moving form of energy, to go from the sun to Earth. Now, it's interesting. You can see that, for example, Saturn is about 10 times as far away from the sun as is the Earth, and then Uranus is about 20 times as far away, Neptune about 30 times as far away. And so you can sort of do the math kind of easily. If it takes 500 seconds, a little over 8 minutes, for sunlight to travel from the sun to the Earth, it would take about 500 or so. It would take about 5,000. It would take about 5,000 seconds. It would take about 5,000 seconds for sunlight to travel from the sun to Saturn. Well, that turns out to be an hour and 20 minutes. To give you some idea, it takes longer than you might think for sunlight to go from the sun to the various planets. 2 hours and 40 seconds to get to Uranus, 4 hours to get to Neptune, etc. The point is that there's a huge distance between the planets and between the sun and the various planets, even in our solar system, to say nothing about distance between the stars and distance between galaxies. Now, a little bit about, now some numbers, planets by the numbers. And if we look at the row in this table for Earth, and to make things easy again, just as we did one astronomical unit, value 1 for the distance between the sun and the Earth, let's say that the mass of the Earth is 1 Earth mass value, instead of giving you the mass in actual kilograms. So let's say it's 1 Earth mass value. And let's also say that the Earth has 1 Earth radius value, to give you some idea of the size and the mass of the other planets. And you can see, if you look carefully, that the planet that is most similar in both mass and radius to Earth is actually our neighbor Venus. It's about 80% as massive as is Earth, and about 95% the radius of Earth. So it's somewhat similar. And you can see that the other 2 terrestrial planets, Mercury and Mars, are smaller. Mercury is about 5.5% as massive as Earth, and Mars about 10.7% as massive. And they have a smaller radius, as you can see as well, compared to planet Earth. The next 4 planets, Jupiter, Saturn, Uranus, and Neptune, are much larger. You can look, if you look at the radius column, you can see that Uranus, if you look at the radius column, you can see that Jupiter, as you've always known, is much larger in size. Its radius is 10.8, almost 11 times as great as that of planet Earth. Saturn, not too far behind, is about 9 times the radius of planet Earth, and then Uranus and Neptune, similar in size, about 4 times as large in radius. And likewise in mass, Jupiter is over 300 times as massive as planet Earth, and Saturn about 100 times, or 95 95 times as massive as planet Earth. And Pluto, as you can see at the bottom, even if we were to still consider the planet, is much smaller. It's even smaller than Mercury in terms of its mass and its radius. You'll also notice the last column is the density, and we said that the first 4 planets are terrestrial planets, meaning they're harder, they're more rock-like, and you can see that they're more dense. These have larger values of density, about 4 to 5 grams per centimeter cube. The point is, it's a number larger than 1. Whereas if you look at the next 4, called the gas giants, they are much less dense, a density of closer to 1, which is actually the density of water, which is actually the density of water. So that is one way. So that is a reason we call the last 4. So that is the reason we call Jupiter through Neptune gas giants, because they're not really, because they don't have the density of the 4 terrestrial planets, and they're more gas-like. Now we'll stop and come back to this slide in our next video lecture, in which we'll talk about how the solar system was formed. So see you in a short while after you take a quiz.